Thank you, Amanda. Hi, everyone. Are we all settled now? We're a bit further forward. Jack, you didn't get the instructions. Sorry for picking on you. Jack works with me. This talk is using Python to make learning Python better. And the idea for this talk came from, I guess, my philosophy of education, which is that education is this feedback loop that is constantly improving over generations. As we teach more effectively, students learn more effectively, and they're able to teach more effectively. And this feedback loop is something that we can contribute to. You all can make learning Python better, and I'm going to talk about how we can use Python to do that. So this is a talk about practical coding for educators. And to get a bit of a sense of who is an educator in here, who here is a school teacher? Hands up. Awesome, thank you so much. And who is a university educator or tertiary educator? We got two, we got a couple, cool. And who is a professional who is interested in education? Cool, lots of you. And who is a student, school or university? Cool, thank you for coming. So I have not turned off my screensaver. I'll just be touching my laptop a lot then. G'day, I'm Ben. This is how I start all my talks, by saying g'day. I work at Grok Learning, where we build a platform that teaches school kids and university students to learn Python and other programming languages. So what I do is I think about teaching and learning with computers. And part of that is professional practice, and part of that is academic as a student, a PhD student. And this kind of feeds into what this talk is about, and what I do all the time is thinking about teaching and learning with computers. So this talk is broken up into three main parts. We've got a bit on computational thinking. So I'm going to talk a bit about computational thinking and how I see computational thinking. I'm going to talk practicalities, how we can use Python to make learning Python better. And I'm going to talk about the future and how we can build effective technology and how we can build communities of practice. So computational thinking. There's a lot of definitions of what computational thinking is. And I have sort of my own opinion about what computational thinking is. And I like to think of it as a literacy. And the reason I think of it as a literacy is that computational thinking is all about using representation systems. So about using a representation to describe something that is computable. So what is computable? Well, if you had have asked Alan Turing, he would have been thinking about mathematics, maybe models. He would have been thinking in that kind of way. But nowadays, we see many more things as computable. We model all sorts of processes, including social processes. And we also see things like games as computable. Not everything that traditionally we would think about as computable is computable. So when we think about that, computational thinking, I see it as using a representation to communicate a computational idea. So some representation that would typically be code, but it could also be written language. And this, to me, speaks of a literacy. And this isn't just the skills of writing the code, but it's the actual representation. And if you think about the way we write language, written language is a representation that we use to communicate an idea. And we can communicate computational ideas using written language. For example, who here has done the exercise where you try to describe making a sandwich? Hands up? Yeah. So if you use written language to describe making a sandwich, it's not great. It comes out pretty badly. But if you use pseudocode or a kind of code-like representation, then that's a great way to communicate a computational idea. So I want to read to you from a book that I've invented. It's called A Future History of Computational Thinking. And this is how I think about computational thinking. So in the 1900s, the concept of automated computation moved from an idea to a reality. At first, only the most accomplished mathematicians, engineers, and academics were able to use these machines. Soon, it was discovered that making these machines programmable allowed people with specialized training to design programs. These programs could help programmers to compute anything of their choice. Over time, programmers developed more complex programming languages. These programming languages were representations that allowed them to communicate a computation to a computing machine. With developments in technology and programming languages, soon every person in the world had access to a computer, and more people were programming. However, they hit a stagnation point. The programmers could develop specialized programs to do many computing tasks that people wanted. Sometimes, this was frustrating for those people. Sometimes, the programs didn't quite work the way they wanted, but people couldn't see the possibility of programming for themselves. Programming languages were hard to learn, and most people didn't have the time to learn them. So they struggled with software that wasn't optimized for them. They continually repeated tasks their programs couldn't do. They rejoiced for the time computers saved them, but hated them for the power they took away. This was the dark ages of computing. Much like scholars and scribes controlled literacy in the distant past, programmers controlled computation. Nobody saw how the world would change when everybody had the power to automate or compute any problem they faced. Can you imagine? There was a time when surgery was done by humans, when everyday people couldn't model or analyze data, when communication about ideas was entirely by essay. There were some who saw the truth, the power of computation. These academics banded together under the banner of computational thinking, advocating for everyone to learn programming. They saw a future, however obscured, where children programmed computers and came to understand the world. Fortunately, that period ended with the rise of computing teachers. Through those great heroes of literacy, computation was available to all. A new revolution was underway, the computational enlightenment, and now we all tweak, hack, and model our way through life. Nobody is left behind by automation because everyone has the power to automate. That is a future history of computational thinking, a story I made up. And this is how I see computational thinking. And this is how I think about it. It's this thing that can totally change the way the world is. And that's what we're doing. That's what we're all interested in doing, is helping more and more people code and learn about computational thinking. So computational thinking, it's the future, is what I'm saying. So let's get a bit practical. My talk is a practical talk, and I will be doing some semi-live coding, so watch out. I'm going to start with a point. If we, myself included, believe this about computational thinking, about coding, about its power to transform the world, then we should practice it. If we're teaching and learning, but we're not using our powers of computing to do that, then what's the point of it all? So this is my main point of this talk. If we believe that computational thinking is powerful and that it's transformative, we should be doing computational thinking about every problem we come across. So that means we should be making our own technology. First off, expertise makes good technology. Many of you are experts as educators or as professionals. And if you have an expertise and you've practiced education, then you're going to be really great at making good technology. Technology isn't something that you can just hack together without an understanding of the field. Many people see technology as just taking something that exists and putting it on the internet or putting it on computers. And if we take a textbook and put it on a computer, it's not necessarily a more effective textbook. But if we take our expertise as teachers and learners and put that into code, that's a much more effective way to make good technology. My second point is that technology doesn't have to be an app. Often we think about programming as building apps, as building web applications, as building something tangible that has a user interface. But Programs were useful long before user interfaces were around, and you can make a program that is useful for your purposes with just text. Finally, you're an expert. Whatever you're an expert in, you're probably an expert. And if you're a teacher, you're an expert teacher. You can use Python, which is this thing you're here to either learn more about or share your own knowledge or practice. You can use Python and your expertise in educating or as a learner to improve your own practice. So I want to talk about my first example, which is building on prior knowledge. So the idea of building on prior knowledge is that when a student comes to a class, a course, any kind of learning, they bring with them prior knowledge. So they have some ideas, they have some knowledge that they've come to the class with. And it's very effective to take those students and their prior knowledge and figure out what the next step is. And this is often referred to as keeping students in their zone of proximal development. We want students to start where they're at and then continue forwards. But unfortunately, it's very difficult to figure out where each student is up to. If you were to spend, say, a few minutes with each of your students at the beginning of every class, that would take your whole class. That would be even more impossible if you're a university lecturer and you have 1,000 students. So if we want to build on prior knowledge, this feels like a problem that can be solved with computers. We can give a program to every student to see where they're at. And so that is what I'll be demonstrating. This is a program called priorknowledge.py. And my process with coming up with this program was to keep it really simple. I wanted to use concepts that I thought everyone here would be familiar with. And so mostly I stick to print statements, input, and if statements. So let's have a go at running this program. From the audience, how readable is this? It's good? Great. So I'm going to run prior/priorknowledge.py. So it starts out by asking, have you done any programming before? This is a great question to ask a student who's starting a programming course. If they've never done any programming, then we say that's totally fine. This course doesn't expect you to have any experience with programming. How about you start on this activity? Now I'm going to run it again, and I'm going to say, yes, I have done some programming, but I have not done any Python programming. Great. Well, you need to learn about Python syntax. So try doing this activity that is at a real website. Then I have done some programming. Have you done Python programming? Yes. So now the program is going to start testing the student to see where they're at. So they have a program, name equals input, what is your name? Print hello name. If I run this program and type in Julia, what will the program print out? Throw to the audience. Yell it out. Hello, Julia, great. Hello, Julia. So next up, we've got another question. I want to make a function that turns minutes into seconds. There are 60 seconds in a minute, so we need to multiply the minutes by 60. Fill in this code. So we've got a function that we need to fill in. So I don't really know much about functions, but I know how to print something out. So I'm going to print out that it is minutes times 60. But it looks like I got it wrong. I was meant to return instead of print. So it looks like I should practice functions. Now this program is very simple. It starts with some print statements. It asks for their experience. If their experience was 3, so if they don't have any experience, then they're going to do the getting started activity. If they have done Python programming before, then we're going to continue on. If they have not, so if N is in done Python answer, then they should start with the lesson on learning Python syntax. And this program goes on like this, just checking the result of each answer, and if they pass it, then they continue through the script. And if they don't pass it, then we say, okay, well now we've reached the point where you're being challenged, and so you want to learn this concept. You want to start on this activity. And this is a really simple idea, but it can be really powerful. So how could you use this idea of building on prior knowledge? Well, you could use it for differentiation. A lot of students, a lot of educators find that their students are in these totally different cohorts where some students are so far ahead of their peers that it's just impossible to find things for them to do. And the other students then kind of fall to the wayside where you end up spending a lot of effort on finding activities for these students who are really gung-ho. But there's also many levels of differentiation amongst the students who are struggling. Some of them may be struggling with variables, some of them with if statements, etc. And using this idea of question-answer, we can figure out where they're at without having to have an actual conversation with every single student. We could also use it to figure out a project that's appropriate for a student. And this could be based off interest, or it could be based off where they're at, where their skill is at. We could use it for reflection, asking students to reflect on what they've learned. We could use it for extensions. When a student finishes their work, when they're struggling to find something to do, you give them the extension script and it comes up with ideas. And this is really simple. This is a Python program that I'm sure most of you understand and could write. It's kind of the most basic level of writing Python is doing some print statements, reading some input, doing some if statements. And it's really powerful. It is automated, so it automates these problems that you have. And it's shareable. This is something that you could give to a peer, to a colleague, to someone who's also struggling with the same problems that you're having, and they could try it out in their classroom. And then they could extend it. And that's what I think is really cool about this, is if we can take programs like these and share them amongst each other, we could extend them and make them better. And this community of practice would help us to teach these things more effectively. So my next slide is about giving feedback. So an example of giving feedback might be to say, geez, Ben doesn't know how to put text in a box, but it's entirely intentional. It's very cool. A better example of feedback would be constructive feedback as a student is learning. When they're struggling with a problem, we want to be able to give them feedback about how they're going. Now, unfortunately, that's really difficult, and we get trapped in these really long cycles of feedback, where a student finishes some work, and then they hand it in, and maybe a few days later they get feedback, or even a few weeks later they get feedback. And by then, the work is totally out of their mind. So something that Grok does, if you're familiar with it, is it has automated testing. So we will test a student's program and give them feedback. Well, I'm about to give away all our secrets and set you up to do this yourselves, and you won't need Grok anymore. So there's a library called DocTest, and it comes with Python, and it's super handy. It allows you to write tests in the documentation for your Python. Here's an example. So this is a minutes to seconds function, much like the one we saw earlier. And this program converts minutes into seconds. Now, within that documentation, I've written an example of how it can be used. So if you use minutes to seconds with 1, then it will return 60. If you use minutes to seconds with 5, then it will return 300. Now, at the end of this program, I can just add a little bit of extra code, and I'll show it in a minute, that tests this program automatically anytime it's run. And if this test case, the minutes to seconds 160, doesn't pass, then it will tell you that it's not passing. And we'll see a bit more in practice how this works. So I've come up with this small project. The idea behind the project is that there are many criteria that determine whether an animal is endangered. One of the simplest criteria is based on the population of mature individuals. So that's adults who are out there and existing and surviving. So this criteria is used if the population is stable. So if the population is decreasing, then there's a different criteria. But if the population is stable, then this is the criteria used. This is a very simple mapping from a number to a category. If the population is 0, then it is extinct. If the population is 1 to 50, it is critically endangered. Probably if the population is 1, it may struggle. 51 to 250, endangered. 251 to 1,000, vulnerable. 1,001 onwards, lower risk. So I've defined this function, categorize, and the function takes the population of an animal. It then returns the endangered category of that animal based off the table above. So that's the table you saw before. So if we take categorize 55, then we would expect it to be endangered. So this little bit on the end that I've added here, that's the bit that does the testing. So that's just 3 lines of code, and what it's saying is this little under name, under main bit is a bit confusing, but what it means is if we're running this script, so if it is running rather than having been imported, which are the 2 ways we can run a script, then we will import DocTest, which is this testing library, and it comes with Python, and we'll test this module. So let's go have a look at how that works. So in step 1, I have this function, categorize, that categorizes 55 and expects endangered out. Now, I'm just going to change into the endangered directory. So if I run this, python endangered-step1.py, if I run this, I get no output. That means that the test's passed. So I'm just going to run it with -v. So it says 1 passed and 0 failed. -v means verbose. So if I were to instead have pass here, so that was the example that I gave before, and that's how you would pass this Python program over to a student. So I run it, and now I get 1 failure. So 1 item had a failure. The example was that we wanted to categorize 55, we expected endangered, and we got nothing, and that's because there was a pass here. Now, let's try this next step, step 2. In this step, I've added more tests, so it's much harder to pass this program. So there's the categorize 55, which gives back endangered, but there's also categorize 0, which gives back extinct, categorize 8, which gives back critically endangered, categorize 105, which gives back endangered, etc., etc. So I have 1 test case per each of those categories. Now, I've just still got here return endangered. So let's see what happens if I run python endangered step2.py. Cool, so test failed. There were 4 failures. So why did it fail 4 times out of 6? Well, if we go back, we can see that extinct got endangered, critically endangered was expected, but we got endangered, vulnerable was expected, we got endangered, lower risk was expected, we got endangered. So there were 4 failures. The 2 cases that expected endangered passed. And so this program kind of works. It's good at saying that things are endangered. It's not very good if they're not endangered. And we can fix this up. So if I fix this up, and I have the full elifs for each of these cases, if the population is greater than 0 and less than 51, critically endangered, etc., etc., and I run step3.py, we can see that it passes all the tests, and if I run it in verbose mode, we can see 6 passed and 0 failed. Now, unfortunately, the downside to this way of doing things is that there's this really big string at the top of the function. And if you handed this over to a student, they would be like, where do I put my code? So what you can do is you can put this string at the top of the file instead, and then it can test every single function in the file. So here I've got a file that you might hand over to a student that includes the description of the task, the categories, and then instructions on how to run the tests. And finally, it has a test for each of these categories, the ones we saw before, along with tests for boundary conditions. And this is the area where students are most often going to get tripped up. So at the boundary of extinct and critically endangered, at the boundary of critically endangered and endangered, and et cetera, et cetera. So if we run this one, Endangered step 4.py, I think I've got it all implemented, yep. We still get the same 0 output, and if we run it in verbose mode, we've got 12 tests, and they all passed. We can do one more tricky thing, which is we can have a text file which has extra tests in it. And this text file is something that we can keep to ourselves and not give to the students. And this one then has extra tests that you might want to have in your back pocket for students who have finished all the tests but maybe have done some tricky things like hard-coded one of the answers. So this one we can run with Python-m, which means I'm using a module and I'm going to use the DocTest module. And then I can use test-endangered.txt. And that, of course, did nothing because it worked. But if I put out verbose, there were 3 tests, 3 passed and 0 failed. So this is how you can use DocTests to give feedback to your students as they're working on their projects. So one of the cool things about this, I think, is that when I think about learning, what I really want is for every single student to get 100%. Now, that sounds absurd, right? There's no class where every student gets 100%, but really that's what we want. Every student should have learned all of the material in the course. And this kind of scaffolded project, where we give them every single test that we want to check, should help students get closer to that 100% mark, because they know the criteria that you're marking against, and they can test their own program with that criteria. My third example is called building a learner model. And this example is about this idea from the education literature called a learner model. And a learner model is a model of a learner. Very straightforward. So the idea is that when we learn a concept and we get better and better at it. And then concepts build on concepts. And we can construct a model of how we think that these concepts are built up. So a very simple model would be that we have a bunch of totally disconnected concepts, like we might say algorithms is a concept, we might say that data structures is a concept, and that students will get better at these concepts over time. So that's a very simple way of thinking about it. So what we can do with this idea of a learner model is we want to help students understand what they know. And this is really important because students often don't understand what they know. There's this effect that everyone has, which is the fluency effect, which is if you recognize something, you think that you understand it. So if you're testing yourself and you say, oh, how does a function work? What's recursion? You think, I remember that word. And then you say, I don't need to test that. I remember how that works. And everyone gets tricked by this. So what we want to do is help students understand what they know and what they don't know. And on top of that, we can use this idea to help us understand what our students know. So a very simple way to do this idea of learner modeling, which I think is a more advanced version of what I've been doing in this talk, is we start by writing a list of concepts in the course. And this could be very fine-grained, or it could be big picture concepts. And then each activity that students do, we map the concepts to the marks of the activity. So if a student does an assignment, then they get a mark for each of the concepts rather than a mark overall. Finally, we analyze this data to understand their learning. So if we know what marks they got on each concept, then we can understand where they're struggling. And we can understand this for each individual learner, but we can also understand it for the whole cohort. So I've got this final example, this learner model, and this one is a bit trickier. I do some stuff with CSV files, and so if you don't understand it, that's fine. I've got all this code on GitHub, and you'll be able to grab it later. But in my learner model, I've got a read and an update. So I'm just going to start by running it. So Python update.py. So this says, which concept are you updating? So I've learned today, I did an exercise on algorithms, and my score out of 100 on algorithms was 55. So now I want to see where I'm at. I run read.py, and it says algorithms. The more you practice, the more you learn. So you can see the three little equal signs on the left is you're getting there with algorithms. So then if I update it again, and I am updating algorithms, the score I got was 80 this time, and we run it. I'm doing well. I should keep practicing algorithms. And you can continue this on and on. And this data I'm storing in a CSV file. So you can see here for algorithms, I got 55, and then I got 80. And so you can go back and you can recalculate how you think a student is doing. You can get your students to give you their scores, or you could enter them yourself. So I'm going to do this again with another concept. Which concept am I updating? Data structures. And I got a score of 90. I'm great at data structures. And read it out. So now I've got two scores: algorithms, doing well, keep practicing; data structures, the more you practice, the more you learn. Now I got 90, so why is it such a low score? Well, one score isn't a particularly good predictor of success. A student may do really well the first time you test them on a concept, but then forget it much later. And so the algorithm I've developed here is relatively simple. It's in read. It takes their scores, and the first time, it just divides it by 2. So they probably, even if they got 100, they probably don't understand it 100%. And then I go on and I add their existing knowledge with their new score and do a kind of running average. So eventually they'll get to 100%. So that's the idea of a learner model. And a learner model could be extended. This is something that you could use with your students, but you could also get it to connect to, say, the Google Sheets API, which it turns out is not that hard to access. And then your students, when they enter their scores, it gets updated to your spreadsheet that you have of all your students' scores. You could extend this to do some data science on it. You could try and understand which students are struggling the most, which students are struggling the least. You could try and understand what concepts are the most difficult for students. And this will kind of fall out just by collecting that data. And it's often the case that once you start collecting data, you're able to use it in ways you never really thought. So, what does this look like in the distant future? Well, one of the cool things I think about programming is that we can solve our own problems. It's really great if there's a piece of software that does something that you want. But it's really frustrating if that piece of software doesn't quite do what you want, if it doesn't quite do that little thing that you want to add on. And that's one of the fantastic things about programming, is we can go and take our own problems and we can solve them ourselves. And one of the other things that I think is really cool about doing this kind of thing is that we can make learning more effective. Computation is this superpower that we as programmers all have, but sometimes it feels like we don't really use it to its full extent. And by taking your expertise and applying programming to it, you can make that domain even better. And finally, I think that with ideas like this, we can build a shared practice. Programs are really easy to share. I've got all of this code that I've written up on GitHub. It's easy for you to grab them and download them. You could make commits and upload, push your own changes. You could fork the repository and make a version for your classroom. You could come up with something that you think is even better than all of my ideas, which is probably going to be the case because these were just the things I thought of. And then you can take that and we can share it and we can all benefit from it. And that's the fantastic thing about open source software like Python, is that we're all able to benefit from the development that other people do. And that's something that I think is really cool that we could all be doing as educators. So finally, hopefully, if we all engage in more computational thinking practices, then my fake history of computational thinking will become a real history of computational thinking. And it won't be a joke. It'll be stuff that really happened. This is where you can get the code from my talk. And now I guess I'll be taking questions. Thank you. So if you have a question, just raise your hand and Bruce will come over. Everyone's super keen for morning tea. No questions? Cool. Yes?
I'll just give you the mic so we catch on.
Yep.
I'm curious how much the Grok platform uses
Yep.
some of your ideas in giving students feedback. I haven't done much tutoring this year because I
Yeah.
just started.
So the basis of the Grok platform is automated testing. And this is something that we think is really powerful for students, is being able to see when their code is working and not working. One of the hard parts about giving feedback is that we in Grok tend to give feedback at the point when students are marking their solution, right? So we say whether they've got it right or wrong and what cases they failed. But often students need a bit of feedback earlier than that. Often students are running code and they don't understand what an error is, or they don't know what to write, or they're kind of stuck in that blank text box, I don't know what to do. And so I think there's definitely way more things that we could be doing to give more structure and more feedback during those earlier processes. And then also something else is that automated testing isn't great at doing things like code quality. A student could write something that is absolutely atrocious but passes all our tests. Just about every year we find a student who has written a series of nested ifs, about 100 if statements long, that they've used to emulate a for loop. And this is not a joke, this happens. And that's the kind of thing where an automated test, we only test so many cases, and so you can just keep writing if statements until you get past all the tests. Any other questions? Cool. Thank you very much.